Okay. So just a quick thing. Depth first is you keep going deep. That means keep going down and down as long as it can connect. Like here, right? It is able to connect up till E. And after that, you backtrack. We spoke about backtracking also. You backtrack and see any other possible route is there. So here, if you see, we go up till E, then we backtrack to C, we backtrack to B and see that there's another alternate route to D. So that is your order. So your order of depth first will be A, B, C, D. A, B, C, E, and then D. And how do you actually implement depth first search? You need to use a stack. Right, we talked about stack also, because you need to for backtracking, you will have to pop out the element and go and search for the next previously available set. Okay, we will come back and visit depth first search again, because your chapter 6, which we are going to start today, is all about depth first search. So this part we will be doing with more examples. Okay, then there's an alternate way of doing, which is breadth first search. Right? Now, in your breadth first search, what you do is you don't go deep, right? You don't go, when I say don't go deep, right? Say you start with 1. In depth first, DFS, what we did, we went up till the last possible connection. Then we came back and saw the other routes. But in breadth first search, you're covering the breadth. That means what? All possible available routes from this matrix vertex, you're upfront covering. So you will do 1, right? Then you will do 2, 4, and 5, right? So you will start with 1, okay? Then you will cover all the immediately connected vertex. So you will do, so you will have 1, then you will visit 2, 5, 4. Here order can be anything. We said you can have different results. Like some of you may do like this, 4, 5, 4, 2. This is also correct, okay? As long as that matrix is there. So we do this. After that, what do? Then you go ahead and extend. So we covered all of this. Now you go ahead and extend. From here, all the possible direct connections. So from 2, only the direct connection was 3. So you will have then 3. From here, right? So we had already visited 1, 2, 5, 4, right? So now we are checking. From here, we visited this. Then from 4, we can visit 7. And from 5, we can visit 6. So that's how you're ordering. So you have 1, 2, 4, 5. Okay. Then after that, you check from these 3, what are the other connected ones? So you get 3, 6, 7. Then you check again, are there any other thing left? So all the green ones are already covered. So from 3, we don't have anything. From 6, we don't have anything. From 7, we have 8, right? So you go ahead and connect 8. Then again, from 8, you go ahead and connect 9. I think that this is pretty straightforward, okay? So how do you implement this? We implement this using queue, okay? So queue data structure, I think you all know what does queue mean. Queue means I can add an element in the first, okay? So I keep adding here. So my addition is at the last. So it is last in, right? If I have to add anything, it's a queue, right? So in a queue, where do you go and stand? You don't go front or somewhere in the middle, right? You always go and stand at the end of the queue. And who gets whose work will be done first in the queue? Whoever is in the first, right? So first out. So last in, first out. So this is the queue, right? So what we do, we use this model to do breadth first search. So how do we do that? The first vertex that you want to visit, put it in the queue. Okay. Then all the direct connected vertices, that means 2, 5, 4, put it in the queue. Okay. Now what you do is you go ahead and check. So by doing this, by putting 2, 4, 5, right, we have finished processing 1, right? We finished all the direct edges which are coming out of 1. So we are done with 1. You remove 1 from the queue. Okay. So next, after that, you check your second element. So pick 2 and see what are all the direct edges coming out of 2. So what are the direct edges coming out of 2? 3, right? So we go ahead and add 3. Yeah, right. So we have so much we have already added. Now we are checking this one. So we know that 3 has come. So I added at the end, right? So with this, 2 has finished processing. So you can remove 2 from the queue. Okay. So now we are left with 4 and 5 in the queue. So you pick your 4 and see what is it that's coming out? 7, right? So you add at the end, you add to the 7 and you remove 4. So now you pick again 5. So you say what is coming out, you add 6 and you remove it from the queue because you finished processing this. And then you go ahead and now pick 3. Anything coming out of 3? No. So you have finished processing 3. You pick 7. Anything coming out of 7? Yes, you have 8, right? So you add to the queue and you remove 7. Then you go and check 6, right? Anything coming out of 6? No. So you finished it. Anything coming out of 8? No. 9 was already, right? There is 9, right? So 9 is coming out of 8. So you go ahead and add 9. You finished 8. And anything coming out of 9? No. So finally you will finish this also. So let me take one more example and do it for you. Let's take an example. Six. Okay, let's take this graph and see how we can do breadth first search. Okay. So just maintain a queue. This will help you. So what do you first put in the queue? Pick any element. So here there's nothing called you have to pick only one. Okay, your number cannot even have, say, you may have something like 21 here, right? So you can pick any vertex. So let us start with, say, 5. I'll start with 5 as my starting vertex. I put 5 in the queue. Then I need to process this, right? So how do I process? I check all the directly coming out elements from 5, right? So I add 21, 6, 3 in the queue. So now I'm done with 5. I can remove it. This is no more in the queue. Okay. So now I pick the next element, 21, right? I'm here. I check what any direct elements coming out of this. Yes, I have 7, right? So I add 7 in the queue and I remove it. I'm done with 21. Then you pick 6, any direct element coming out of 6. We have 3, but the moment you put 3, it will become a loop, right? That's one way of visually checking. The other one is you already have 3 in this queue, so you cannot add it, right? So we are done with 6, but we are not adding anything. Nothing is left for us to add. Then you pick 3, okay? Anything coming out of 3, yeah, 6 is there, but that's already processed. So there's nothing extra to add for 3. So now we are done all of this, right? So this is the order of your breadth first. You will be visiting like this. 6, 3, 7. Now go to 7 and process. Anything coming out of 7? Yeah, we have 9. Add that to the queue. Now you can remove. I'm done with 7. Okay. So next, pick this 9. Anything coming out of 9? Yeah, you have 2 coming out of 9, right? You have 10 and 11. 10 and 11. I'm done with 9. Now pick 10. Anything coming out of 10? 11, but it's already in the queue. So there's nothing extra. Then for 11 also, there's nothing extra. So what is the order of your breadth first search? You will visit 5, 21, 6, 3, 7, 9, 10, and 11. So this is the traversal. When you do breadth first search traversal on this graph, you will visit the vertices in this order. Okay, given that 5 is your first vertex. I hope this is clear. Any doubts on breadth first search? Any doubts
No,
on depth
ma'am.
first search? Okay,
No,
good.
ma'am.
Let's do the same thing using DFS also, because I want you to be freshly aware with DFS, because the next unit 7 is all about DFS. So let's do the same example using DFS also. Okay. So let's solve this using DFS, depth first search. Now for depth first search, we will use stack. Stack is whatever you put in, you will take out from the top. Okay, last in, first out is your stack. Okay. Okay. So here also you can pick any vertex. So let us pick 5 only, so we can understand the difference between DFS and BFS. So let's pick 5. I put 5 in the stack. Okay. In depth first search, you have to keep going till the depth of the vertex. Okay. Say now out of 5, I can pick anything. I have 3 choices. I can pick 6, 3, or 21. Which one do you like to pick? Yeah. Do you like to pick 3, 6, or 21? You can pick any. Okay. You have 3 choices.
6.
Okay. Let's pick 6. So I'll add it to the stack. So I visited 6, right? So from 6, what are the options? Where and all can I visit?
3.
3. So what we are doing here is whatever is on the top of the stack, we are processing that. Okay. So what I did was first 5 was in the top of the stack, right? So I processed 5. Okay. And I said, okay, let's do 6. Okay. Now from 6, 3 is, I'm able to process 3. Right. Now from 3, because I always have to look at the top element of the stack. So from 3, is there anything that I can process?
No, ma'am.
No. It's already visited. Very good. So we stop here. So there's nothing more to process on 3. So I am going to remove it from the stack. Right. So let me take it. So we've visited 5, 6, 3. So I'm going to empty it from the stack. Okay. So my stack now contains only. So this is backtracking. Now you understand how we are backtracking. We were here, then we went here, then we went here. Okay. Now we are done with 3. So we are coming back to 6. This is the concept of backtracking. And that's exactly what your chapter 6 is. It's all about backtracking. And because DFS helps you backtrack, that is why we will use DFS as a mechanism to implement backtracking. Okay. So now we are back to 6. What we have to do, we have to see from 6, is there any other option possible? No, right? Here we don't have any option. So we remove it from the top of the stack. So that means now we have gone back to 5, right? So now from 5, we see, is there any other possible option to go? Yeah, we can go to, we can't go to 3 because 3 is already processed. So we go to 21. Okay, so I add 21 on top of the stack. Okay, so from 21, what can I process? Because I always have to look on top of the stack, right? So from 21, I can process 7. So I add that to the stack. From 7, I can process 9. So I add that to the stack. Okay. From 9, I can go either ways. Let me pick 11. I add that to the stack. So what are we visited? 7, 9, 11. Okay. Now after 11, can I visit anything? Yeah, it's still possible. I can visit 10. So I add that to the stack. Right. Now from 10, I can't visit because I only option left is 9, but that's already visited, right? So I can't do 10. So I'm done processing 10. There's no other option for me, so I remove it. So I'm going back. Now I have 11. I check any other possible routes from 11. No, we have finished everything. So I remove from the stack. I go back to 9. Any other option? Yeah, we have an option 10, but that's already covered. So there's nothing left to process on the 9. So we go back to 7. Again, we check anything on the 7? No. Go back. Anything left on 21? No. And finally, anything left on 5? No. Right? So we have emptied the stack. So this is the order of DFS traversal. I hope this is clear. And now you understand how DFS helps in backtracking. Okay, so with that, let's go to the fresh chapter. This is the last chapter in your textbook, which is Unit 6. So if you see, we have skipped chapter number 4, which is dynamic programming. We'll come back to that. We'll finish off backtracking because I thought now you're familiar with DFS, right? So it was more logical to finish backtracking and then go back to dynamic programming. So what is backtracking? This is an application of DFS. Okay, we know how DFS work, but where can DFS be used, right? So there are some problems, there are some computation problems, right, which have you need to build incrementally. You need to build the solution incrementally. Okay, now how does backtracking help? In backtracking, while you're solving the problem, suppose you have built this, then you go ahead and build this, right? At some point when you realize that, okay, now by going this way, continuing this way, it is not going to lead to a proper solution. What you do is you go back to the older subset, small set that you had built, and you build a new increment on top of it, right? You keep building this. At some point, you will realize this option was also wrong, right? So you again go back, right? You pick the previous correct option which was there, and then you build an increment on top of it, right? And you achieve it, right? So this is same like how we did greedy algorithm, okay? The difference, so there will be one question which you may come across. They will ask you to explain the difference between greedy algorithm versus backtracking. Right? Because greedy algorithm was also building your solution in small steps, right? Step by step, it was building. So as you keep building the step by step, you get your overall solution. That was your greedy algorithm. But the problem is greedy algorithm is once you have picked your choice, right? This was my option number 1. Then I picked this, then I picked this. You have no way to go back. Whatever option is picked, that is final. You remember in the definition, we also told the incremental solution that we do is unchanged. You cannot change that. Once it is picked, you have to take that, right? Whereas in backtracking, we also build same step-by-step solution we build, but at points where we realize that this will not lead to the correct solution, we have an option to change that option, right? So here we picked option number 1, say then we picked option number 2 and 3. We realize 3 is not a correct choice. So we have an option to drop that and go back and choose a different option. That is backtracking. Okay, so it uses to solve problems where you have to search a large space. That means your number of input is very high. Okay, and what it actually does is it systematically tries to eliminate possibilities, right? So backtrack uses DFS. We saw this, right? They determine problem solution by systematically searching the solution space. Solution space is all possible options. Okay. Because it is DFS, you have to organize your data in some kind of a tree structure. Okay. Now, backtracking is a procedure whereby determining that a node can lead to nothing but a dead end. That means you hit upon a node, okay, and beyond that, say suppose, imagine it's a tree structure. Okay. This is a tree structure. Say you visited this, then you say you picked this and you went here. At this point, say you realize, oh, going forward, any option I pick will be wrong, right? So at this point, you can discard this complete set. You don't have to go down and visit because, at this point itself, you were wrong, right? So you can discard. You have an option of discarding all these subsets and directly go backtrack and pick another alternate solution. So that's one of the advantages. You can immediately, the moment you realize it's not going anywhere, that means you have nothing but you have reached a dead end. We go back to the parent node and proceed the search on the next child. So we backtrack to the parent node and proceed on the next child. So this way we are stopping, we are unnecessarily not processing anything which will lead to a dead end. Okay. Maybe if we take one example, you will understand this concept much clearer. Okay. So what kind of problems we have in backtracking? We have three problems. Okay. There is a problem statement for n queens problem. There is a sum of subsets and there is graph coloring. So we'll understand what the problem is and we'll see how by arranging in a DFS manner, it helps solve this problem. Okay. So let's understand first what is n queen problem. N is a number. Okay. N is just a number. It is saying number of queens. It says number of queens. So your n can be 2, n can be 4, n can be 8, anything. Okay. So it says those many queens. So n is just a number. So what do you mean by queen? Can anybody tell where we use queen? Any game that where we use queen?
Chess.
Chess, correct, exactly. So this problem is actually talking about placement of the queens in the chess. Before we come here, I think if I don't know how many of you have played chess. So imagine in a chess, you always have this, it's a square. So you have, say, it's actually more. In actual chess, you have 9 cross 9. For now, let us take 4 cross 4 here, right? So the property of the queen in the chess is wherever queen is placed, right? It is very powerful. So it can destroy anything which comes in this row. It can destroy anything which comes in this row. It can also destroy anything which is diagonal. That is why queen is very powerful in chess, right? So if we have more than one queen, say we have now 4 queens, queen 1, 2, 3, and 4. Actually, in the proper chess, you have only 2 queens, but this is like, imagine this is just a queen's problem. So you have 4 queens because the constraints are the same, right? That row, that column, and that diagonal, you cannot place anything. That's why they have picked only same kind of coins or pawns, right? Okay, say queen 1 is placed here. So what is the option for me? Where can I place queen 2? So this is the first row. The other condition is queen 1 is always on the first row. Queen 2, I always have to place it on the second row. Queen 3, I always have to place it on the third row. And queen 4, I always have to place it on the fourth row. Okay. Say suppose we made this choice. We placed queen 1 here. So where can I place queen 2? So this is my row number 2. I have to place queen 2 here only, within this row only, right? I cannot place here because if I place queen 2 here, it will get hit. I cannot place here because if I place here again, it will get hit. Here, I can safely place queen 2. I can place here. I have 2 choices, right? This is also correct. I can place here also. Queen 2. This is also correct, right? Now, suppose I place here, then where can I place queen 3? Can I place queen 3 here? No, right? Because it will get hit with this queen. Can I place it here?
Yes.
It's safe. Will this, see, this queen will hit here. This queen will hit here. This queen will hit here, right? So this is safe. So I can place queen 3. Here also I cannot place. Here also I cannot place. So this is the only option for me to place queen 3. And then let's take a look at queen 4. What is the safe place to place queen 4? Here I cannot place because it will get hit. Here I cannot place because it will get hit with this queen. Here also I cannot place because it will get hit with this queen. Right? Here also I cannot place because it will get hit with this queen. Right? So with this placement, I don't have a choice. I cannot place queen 4 anywhere. Right? So I have to go back and change the positions of these queens. Right? So I know that this choice is wrong. Whatever we did here was wrong. Right? So I have to see, is there any other way where I can place it? So what we do is I'll do that. We'll take a proper example and do it. But now you understood, right? The positions, at least you understood. What is the correct position? What is the wrong position? Right? Everybody understood why we cannot place queen 4 here. None of these choices is correct. You all understood why?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Okay. So with that, let us go to the actual problem and see how to do it. Right? So n queen problem, n is a very generic statement. Let us first define the problem statement for a 4 queen problem. What is a 4 queen problem? Here, n is 4. That means there are 4 queens. So you need to place 4 queens on the chessboard, which is of 4 cross 4 only. Right? So how many ever queens are there? That width of the chessboard you have to select. This is not given anywhere in your question. Your question will be only solve 4 queen problem. Right? From there, you have to derive. You have to derive that there are 4 queens and your chessboard is of size 4 cross 4. Okay? And what are the constraints? The constraints are no 2 queens can be in the same row. No 2 queens can be in the same column. No 2 queens can be on the same diagonal. Right? This we understood. Now you understood what is the problem statement. Right? Just a note here, something like related to the number, like n is 4 and this is 4 cross 4. These are explicit constraints. And the positioning, like any specific constraints that we have, they are called implicit constraints. Okay. So let's look at how to solve this. Okay. So here also we understood. So we understood that you have to place queen 1 on the first row. You have to place queen 2 on the second row. You have to place queen 3 on the third row and queen 4 on the fourth row. So what we will do is we will show the positioning. When I say x1, no, it is the position where I can place queen 1. When I say x2, it is the position where I can place queen 2. Similarly, x3, x4. Okay. So what do I mean by x1, x2, x3, x4? So just take a look at this example. In this, x1, okay, let me just quickly just randomly put some, this is not the actual solution, but I'm just trying to make you understand what will be the values of x. Okay, this is not the right solution, but here, can anybody tell what will be the values of x1, x2, x3, x4, right? So when I say x1, I always mean queen 1. Okay. So what is the position of queen 1? Here, I have to give the column number. Right. So position of queen 1 is 1. Position of queen, sorry, this is 2, this is 3. Okay. This is 2. So position of, what is the value of x2? Value of x2 is 4. Because I have queen 2, which is in the 4th position here. Okay, now please tell me what will be the value of x3?
2, ma'am.
2.
And what is the value for x4?
4.
4.
4, ma'am.
Right. So you understood, right? What I mean by x1, x2, x3, x4. And in fact, this is your solution. This is where you will say the correct position of where the queens can be placed, right? That is your solution. So whatever you come up with the values of x1, x2, x3, x4, this is nothing but your solution. Right? This is not the right solution because there's a problem here, right? This will hit it. So this is not the right solution, but just wanted to explain you the positioning. Okay. So now, then how do we solve this problem? Right? So what we'll do is we will take a breadth first, sorry, DFS approach and see how we can solve this problem. Okay, let's. Now, so here, no, let's see what are the possibilities for x1, right? I can place x1 here, 1, 2, 3, 4, right? So I can place right. So I have 4 choices, right? I can, the value of x1 is 1. That means I can place it here. Or the value of x1 can be 2. I can place it here. Or I can have value of x1 as 3. That means I can place it here. Or the value of x1 can be 4. I can place it here. Right? All, so because it's first one, I have in all 4 choices, I can place queen 1. So let us explore the first option. What will happen if I place the queen 1 here? So this will like this. So it will look like here. When I pick this choice, it is queen 1 here. Okay. So with this, what are the option I have for x2? Okay. So what is the option I have for x2? How many do I have? Really 4 choices for x2? x2 means here. What are the options I have for x2? Can I have x2 equals 1? Do I have this option?
No, ma'am.
No, right? So I don't have this option. So where can I put? I can put here. So I can go ahead and see what happens if I put x2 as 2. Okay. Then I have also a choice. I can put here, right? If I put here also, no problem. There is no conflict. So I have a choice where I can put x2 as 3. I also have a choice here, right? So I have a choice of putting x2 as 4 also. So let us explore each of these choices. Okay. So what will happen? How will it look here? So Q1 will be here. And I'm saying I'm going to place Q2. Okay, sorry, 1 second. We said this is not possible. Is this possible? X2 as 2?
Yes, ma'am.
But it's violating, no? Diagonally it will hit. Correct, no? I can't place here also because we said I can't place here, I can't place here. Even diagonally the queen will hit, right? So even x2 is not a choice for me. Sorry. Right? x2 is also not a choice for me. I can't place here. So the only 2 choices you have. I can place queen 2 here. There's no threat. I can try to place queen 2 here also. There is no threat, right? So these are the 2 choices. So let me expand it this way. So you have x2 as 3 and x2 as 4. These are the only 2 choices you have. So let's further explore. This is saying I'm going to place this choices. I'm going to place queen 2 here, right? So with this, what is the choice for queen 3, x3? How many choices I have? Let's see. Can I place queen 3 here? Yeah, please tell me yes, no.
No.
No. So this is not a choice. Can I place queen 3 here?
No, ma'am.
No, because it hits here, right? Can I place queen 3 here?
No, ma'am.
No.
No, ma'am.
Can I place queen 3 here?
No, ma'am.
No. So basically, I don't have any choice for queen 3, right? So I stop here. You saw this is the dead end. This is the dead end, right? There is no way I can place queen 3. So it makes no sense to go ahead and go choose something for queen 4, right? We know that we have hit a dead end here. That is where depth first helps. I'm not going below this, right? I'm stopping right away here. And the moment you hit dead end, what you have to do? You have to do backtracking, right? Go back to its parent, right? And see what are the other choices. You know that this choice is wrong. This choice was wrong, right? This is a dead end. You have hit a dead end here, right? So this is incorrect choice. So go back to the parent, right? And see, now you have this choice. Let us explore this one and see whether it will help out here, right? So what are the placements here? Queen 1 was here. Queen 2 was here. Now we have to check for queen 3. Sorry, x2 was 4 in this case, right? x2 was 4. Right? So with this choice, let us explore, is there a possibility for queen 3, x3? What are the possible options for x3? Can I place queen 3 here?
No, ma'am.
No. Here?
Yes, ma'am.
Right. So this is possible. So I have an option where I can place x3 at 2. Any other choices? Let's see here also. Is this okay?
No, ma'am.
No, because it's hitting here, right? And obviously not possible here because it will hit here. So I don't have any alternate choice. I have only one choice of putting it here. So let's explore that. Okay. So what did we say? Queen 1 will be here. Queen 2 will be here. And queen 3 will be here. So with this placement, what is the possibility for queen 4? Here,
No, ma'am.
here,
No, ma'am.
about here,
No, ma'am.
and here also not possible. So again here, we have hit a dead end for queen 4. Right? This option is also not possible. So when you hit a dead end, what do? You backtrack. Backtrack and see whether this parent had any other child. We know that this also didn't have no other option at this level. This was the only option, right? There was no other option. So here also, this possibility is also not possible. So we have to backtrack further. Backtrack. Now you see, was there any other choice? This also didn't work. This also didn't work. And was there any third choice at this point? Like, did we have any third option here? We had only
No.
these two options, right? We did not have. So this is also wrong. So I have to go again backtrack. This option also led to a dead end for me. So I have to backtrack. Backtrack and go to the parent. So with this, what we realized, this full set, what we picked, this one that we explored as x is 1, placing the queen at the first position, this is wrong. It will never lead to a solution. So what does backtrack say? Go ahead and explore other child options. Okay. Till here, did you understand why this x1 never led to a solution? None of these led to a solution. You understood till here?
Yes, ma'am.
Yes, ma'am.
So let us explore. I need some space here. So what I will do is I'll just erase this. X3, X4, I'll just keep it here. We'll do this, but I need some space here. So what I'll do is X1 we'll explore this option. There are two other choices. We'll come back to that, okay? Was there, and X1 as 4 was also. Let's first explore this and come back. Okay? Same thing, let's see here. What did we say? We are saying, okay, now your queen is at the second position. we're trying to see possibilities for this combination, right? So with this, what are the choices I have for queen 2? So I'll go ahead a little faster here. If you don't understand anything confused, stop me. So I'm going to check out possibilities for x2, queen 2. What are the possibilities for queen 2? I can't place here. I can't place here. What's happening? I can't place here. I can't place here. This is possible. You all agree?
Yes, ma'am.
Right. So I have only one choice, x2 as 4. I have no other choice. So with this, what I do is I have queen, sorry, not here. I have queen 2 I can place here. Sorry. Queen 1, queen 2. So with this, let us explore what are the possibilities for queen 3. Where can I place queen 3? Here. Is it safe? Is this safe?
Yes, ma'am.
This is safe, no? Correct. So this is safe. So this we will explore. So what we did was this one, and this one. This is safe. We have to further explore this. Okay, we'll see any other possibilities are there. This we saw here. No, right? This is a problem here. No, because this is a problem here also. No, this is a problem, right? So no other choice left for me. This is the only choice. So it's clear for you, right? This is the only choice. So now we have to explore this only. So let's explore for the fourth queen. Right? So I'm going to explore for x4. So here, not possible. Here, not possible. Here. Is this okay?
Yes, ma'am.
Right? This is okay, right? So what did we say? Queen 3, queen 4. This is a safe choice. I can put here. Any other possibility for queen 4? Yeah, this I know it is okay. Here, can I place queen 4?
No, ma'am.
No. Right? It will hit. So no other choice. This is the only choice. So what did we have actually found the solution. We have found the placement for the queens, right? So this is your optimal solution. This choice, right? What you did here is a correct way. So you put queen 1 here, then you place queen 2 here, you place queen 3 here, and you place queen 4 here. We got the solution. So how will you represent your solution matrix? So you need to represent your solution, right? So how will you put? So you give the values for x1, x2, x3, x4. These are nothing but the queens. So what was the value for this? Can anybody say? What is your final solution? What is the value for x1? We said x1 means this. x2 means x are nothing but queens. Okay. So what is the value for x1? Where did we place the queen?
1.
Right. What's the value for x2?
4.
4.
Exactly. And x3. Hey, wait, something wrong.
And X.
Yeah, I did wrong. Sorry. Okay. x3 is 1.
1,
And queen 4 is 3. Right?
3.
So we got the solution. So once you get the solution, you don't have to explore other choices, right? We don't have to go ahead and continue this. Remember, depth first search, this is also one of the reasons why we choose depth first search. Depth first search is you go deep, now you found the solution. So you can simply discard this. You save some time, right? You save some processing time also. So you don't have to go ahead and explore other choices. Okay. Now, if for whatever reason this also did not lead to a solution, then we had to backtrack and go find out for this option. Okay. Now, as a homework, right? As a homework, I want you to go ahead and explore these two choices also. Okay. And see, do you find any other way of placement of the queen? Just to give you one hint, one of these two was, there is a correct choice in one of these combinations also. So please go ahead. Anyways, you have to practice this problem. So go ahead and practice with the solution where, so what does this mean? This is, you're going to try this combination. You're going to try where x1 is 3. That means you will put your first queen here. Okay, go ahead and try this combination and see what happens. And similarly, go ahead and try this combination also, the x4 combination. That means you're going to try and see what happens if you place queen 4 here. Okay, so please go ahead and complete this, because one of these two will also give you a right solution. And in n queens problem, you don't have to get all the solutions. The moment you hit one solution, that is good enough. In exam, if you get at this level, you can stop. You don't have to go further and explore these two. Okay, clear? Is this clear? N queens problem, 4 queen problem
Yes,
is
ma'am.
clear, right?
Yes, ma'am.
Yes,
Right.
ma'am.
So same thing, you can go ahead and explore for 8 queens, 8 queens or 16 queens, etc. Okay, but the only problem is the bigger the number is, manually doing it becomes a lot of options. See here, just with excess, with 4 queens, we had so many combinations, right? Now imagine if you have 16, imagine this box was 16 cross 16, right? You had so many choices. It's very hard for, even if you sit and do, right? You may need 2 hours or 3 hours, I don't know, right? And same thing for the program. That is why we go ahead and write an algorithm for this, and the program will be able to execute it for you, right? But if you understand how 4 queen works, you can understand how any n queen problem will work. Using DFS, right? You saw how DFS can be used to solve n queens problem. We have 2 other type of problems, which is sum of subsets and graph coloring. The problem statements are different, like each one has a different kind of a problem, but all 3 of them can be used, all 3 of them use the DFS mechanism and backtracking to solve it, right? So that is why I wanted to continue these 2 types, because all we need to do is just understand what this problem is and try to apply DFS, right? So the second type of problem is sum of subsets. What does this mean? Sum of subsets, right? So set means what? It's a unique set of numbers. Set always has positive numbers, and in a set, right, generally the numbers don't repeat. Like you can have a set which can be 4, 5, 6, 7, 8, 9. So you can have any number of set. A set can be just one number, right? A set can be, say, 2 numbers, right? And in a set, right, you will not repeat a number. Like, for example, you will not have something like this, right? You will not have repeated numbers. So given a set of numbers, the problem statement is, suppose they give the overall sum as some number, okay? Like, to understand this, let us take one example parallelly, okay? You know what is a set? A set is a set of positive numbers. Example is this one, where you have 11, 13, 24, 7 is a set of numbers, right? Now, and this also they will mention that sum should be some number m, okay? So example here, sum should be 31, okay? Now, what is the problem? You need to figure out what numbers you can take from the set whose sum will be 31. Like, for example, you need to try combinations like 11 plus 13. Will it give me 31? Or say 11 plus 24 plus 13, right? Will it give me 31? You need to find a subset. That is why these are subsets, right? Subset means a smaller set from the actual main set. So find the subset of numbers whose sum is what they have asked for. That is the sum of subsets. Okay. So how do you have to, if some, like I give you the, and you know, this problem is generally asked in interviews, especially from the trees, right? Why I skipped dynamic programming and came to trees is whatever we did in divide and conquer, right? Mainly the sorting mechanisms, quick sort, merge sort. These are any interview you go, at least they will ask you one of the sorting. Okay. And coming to the tree traversals, pre-order, in order, post order, right? They will ask you one of the tree. Sorry. Okay. Yeah, no problem. The trees also, right? Very important. You can get these kind of questions in any interview you go, and these kind of questions will definitely come. I mean, sometimes no, it's a little tricky and people will struggle to solve this problem. But if you know that this is in the category of backtracking, right, you can easily solve this problem. Otherwise, how will you try to solve this? Let's apply brute force method. Let's apply brute force means you try every combination that is possible. You have to try to get this 31. Okay. So just see, I have expanded the possible combinations for you. Okay. Like for example, if you don't know that you can do this easily by depth first search, okay, how will you go ahead and do this? You will pick the combination subset, right? It can be first you pick one number, single number 7. You'll say, is it equal to 31? No. So you discard this. Then you pick two combination of two numbers, 7 plus 11. Is it 31? No. You pick 7 plus 13. Is it 31? No. Then you see, okay, 7 plus 24. Is it 31? Yeah. You got this combination, which was correct. Okay. But you need to find all the combinations, right? So you got one combination, which is subset, right? So you got a subset whose sum was what they had asked for. They had asked for a plus 31, right? This is the correct subset. What are the other subsets you need to find? So now you exhausted with all two combinations. So with 7, what you will do now? You will try with, you will keep 7, plus you will try these two. So you say 7 plus 11 plus 13. This is also correct. So you got one more subset. 7, 11, 30. This sum is also 31. Okay. There are other combinations, right? This is possible. Then you try 11 and 24. 7 plus 11 and 24. This is wrong. It will not give you 31. You try, okay, 7 with say 13 and 24, right? See, I'm just telling you what are the possible combinations, okay? And finally, what you'll do with 7, you will add all, right? This also you will check, right? This is not correct. Then we finished with 7. You had these many combinations, right? Now you go ahead and you can, you have other choices also in this problem. Right? What are the choices? You leave 7 because with 7 you tried all the combinations. So you can remove 7 and try what are the remaining combinations. Like for example, don't have 7 and try with other combinations. Right? 11 alone, 11 in combination of with these two numbers, 11 in combination of all together. Right? This is another possibility. Then the next possibility is you have tried all combinations with this, all combinations with this. Pick 30. Right? You have two choices with 13, either alone or together, right? And finally, you pick only 24 and see. Right? This is called the brute force method. This is like you try every possible combination and you figure out whether this is correct or not. You see the complexity, right? You may forget selecting some subsets which are correct, right? You may miss these kind of subsets. And this will work only for small numbers. The moment your numbers become big, trying out these combinations is very, very difficult. So the same problem, let us apply DFS and see how it will work with. We'll do with this, say, let your subset be 3, 4, 5, 6. Okay. And the sum that you need is say 30. Okay. So first of all, you see this is ascending order, right? So you don't have to do anything with this. Okay. So what will be the initial sum when you start the problem? You have not picked any subset, no? Your subsets are all empty now. So your initial sum is 0. That is why your tree is starting with 0 value. Okay. This part is clear. And anything that you put in the vertex, the value that you put in the vertex is not these numbers. The value that I put in the vertex is the sum. The answer, you can say. The answer, what we get by adding the subset, is what we put in the vertex. Okay. So with this, let us start. Initially, your answer is 0. That means your sum is 0. Okay. So you pick this number 3. So you have a choice. You need to find the sum of subsets, right? So you can form so many subsets, right? So one option is you will build a subset, okay, which has 3. And then you will try to find out all the other combinations. Or you will build a subset which I don't have 3. I'm right away picking other numbers and seeing what are all the combinations. So you have 2 choices starting with first number, right? That is why we are having 2 trees. Okay, one which says I'm picking a option with 3. Okay, so another one is without 3. Okay, so what will be the sum here? With 3 means what will be the sum? So when I say with 3, how will your subset look like? So this is your subset. With 3 means I'm having 3, right? So at this point, what is the sum? What is the sum of this subset? Sum is
3.
3, right? Because you have only one number there, that only you're adding. So sum is 3, right? So when you do with 3, that means when I say with 3, you have to imagine that your subset is something like this, okay? So your answer will be 3, or you can say 0 plus 3, which is 3, okay? When I say without 3, you have to imagine some subset which is not having 3, okay? And we don't know what else it has. So what will be the answer here? Currently, this is empty. I have not put anything in the subset. So what is the answer? What is the sum of this subset?
0.
0. Correct. Right? Because we have not picked any number here. So obviously the answer is 0. Okay. So now let us, because it is DFS, no, we'll go deep into this and then come back and explore this. Okay. So we picked 3. Okay. Now next, what do you have? You have to look at 4. So what options do you have again with 4? Either you will include 4 or you will build a subset without 4. Okay. So if you build with 4, so this is your second, say S2 I already used, no? Some number, some subset. So your subset is now containing 3 and it is also containing 4, right? So what will be the value? What will be the sum answer to this subset? Because it is having 3 and 4.
7, ma'am.
Right. So what you can do, no, instead of going back and tracking, just look at the parent and add to that parent. So you also already know parent is having value 3. So just add 3 plus 4, 7. Correct. Okay. This subset is having 7. When you go without 4, so you're building some kind of a subset. Okay. I'll just call it as 4. You're building some subset. Is it what and all it is having here? Say at this point, if you write this subset, right? Say subset number 4, what and all it has?
Only 3.
Only 3. See, you have, how did you reach here? You went here, that means with 3. So the subset has 3. And then you came here, which is without 4. So basically there's nothing else, right? So what will be the sum of this?
3.
3, because we're not adding anything, right? Just the parent. Wherever it is without, the answer will be whatever was your parent. Wherever it is with, you have to add that with the parent and you will get the answer. Okay. So keep checking this m equals 13. Okay. It's if it is less, you can keep continuing. Okay. Because it's less, we can still further, we can do depth first search. So what is the next choice we have with 5? I will either do with 5 or without 5, right? So if I do with 5, right? So how will my subset look like? What and all will be there in the subset? Look at the tree, how you came here. How did you reach till here? You came here, you came here, you came here. So what and all the subset has? At this,
3, 4,
yes,
7.
3 is correct. Then it had 4. And then, no, see, you need to be very careful, okay? You should not see the vertex. See this comment,
Then 5, ma'am.
right? So don't get confused. Huh? 7 was not there. It
Okay,
was,
ma'am.
you had 3, you had 4, and you had 5, right? So, and then to find the sum, you need to look at the vertex. So what will be the sum here? If you picked 5, so what will be the sum? Just add it with the parent. So it will be 7 plus 5, which is
12.
so we have 12. What is the question for us? M is 13, right? It is still less than 13. So we can go ahead and try one more choice. Right. So we have, it is less than 13. So we can go ahead and try with this also. Okay, before that, you tell me this value of this vertex. So first of all, tell me how will this subset look like? This subset, what and all it will contain? The moment you reach this vertex, how will your subset looks like? What and all vertices will cover in the subset? You should see how you reached here. You came here.
4, 5.
Go from top, right? Go from top. So what and all it had? You came here, right? So it had
3,
3.
4, 5.
Then you came here, so it had 4. Then you came here. Did it have 5 or no? Should I put 5 here?
No, ma'am.
No,
Without
because
5.
it was without 5, correct. So with this, what is the answer that you get?
5.
5. 5. I said if it is without means the sum, you're not adding to anything before the sum, right? Just the sum will remain the same. See, you gave me the subset, no? The subset was what? 3 and 4. So what will be the sum here? 7, no?
7.
Yeah. You don't have to actually add it. Wherever you said, just remember this point, wherever you have without, right? You see here, wherever you have without, the answer will be same as the root. See here, you had without. So the answer was same as your parent. Here also you had without. So answer was same as your parent. Here also it is without. So answer will be same as your parent. Basically, you're not adding anything extra to your parent. Okay. So let us explore last choice. What you have? 6. Right. So we can explore 2 choices. With 6. Without 6. Okay. So here you tell me. With 6 means first you tell me how will your set look like, because you need to imagine how will your set looks like, what and all will contain in the set.
3, 4, 5, 6.
Very good. And then what will be a sum? Just add it to your parent. So it will be 12 plus
18.
correct 18. Right. Now you check. You have to keep checking with your actual answer, right? You need only 13, but you have got 18. So this is wrong. This even if some other choices were there down, you should not pick this. This is a dead end. Okay. So let's say without 6 means what will your answer remain?
12.
12. Right. Now here again, we don't have a choice. This also we have got a dead end. So none of these options will work. Right. Why I'm saying dead end? Because we have finished all the numbers. We finished 3, 4, 5, 6. All numbers are finished. So I cannot create any subtree below that. Right. So now what do? I have reached the end of it, right? So how should I continue the problem? I was here and I reached the end of it. This was wrong. So what should I do now? You have reached the dead end. So when you reach dead end, what you should do? I told you something, going back. So what is that called?
Backtracking.
Backtracking.
Backtracking means go back to your parent and see if you have any other choice. Here I went back, no other choice, right? We finished executing both of this. So I go back to the parent and see any other choice, right? This we have not yet explored. So I can explore this further. So how will this be? What options I can do here? Just give me 1 second. Just answer to this. Oh, sorry, I was muted.
It's
So
okay.
my question was after this, no, what choice you had? So I was saying we have come till here. We have checked here. So we have a choice only left with 6. And then you can either select 6 or you can not select 6. So if you select 6, what I was saying is don't go ahead and keep computing the subset. Do it only when your answer matches. Otherwise, unnecessary.
6
You
or
don't have
5,
to.
ma'am?
See here, no? If you look at this, you finished 3, right? Then at this level, you finished the choice of 4. You were at this level, you finished the choice of 5, right? And you decided not to pick 5. So you finished this. Now you're left only with this. Is it clear? It's 6, not 5. Is
Okay,
it clear?
ma'am.
Yeah.
Yeah, ma'am.
Right. So if you pick 6, what will be your sum? Just add to your root parent.
13.
13. So is it matching what we need?
Yes, ma'am.
Yeah, so this is the right solution. So how did we reach? So the moment you get the answer as correct, right? Now you need to tell how did you reach the subset? What was your subset looking like to get the answer 13? So what you should do, you should trace back, right? So this is the second option. First subset we already built, right? Where we got some 13, right? So how did you reach this 13? You have to do, you tell me, how did you reach 13? How will your subset look like?
3,
3,
4,
4,
5, 6.
See, you pick this, so with 3. You pick this, so with 4. You pick this one, which is what?
Wrong.
Without 5. So your subset will not contain 5. Okay. Then you go ahead and you picked this
6.
with 6. So your subset contains 6. Add and see. 10 plus 3, 13. You got this answer, right? Correct?
Yes, ma'am.
Yeah. So this is your correct answer. Let's quickly do the test and we can stop the class. Okay. So without 6, what will the answer be?
7.
Right? And this doesn't match, so this is not a right answer. Okay. So now we finished everything. So what you do in the depth first search, you go back to your parent, you go back here, and now you have one thing that you need to process still, right? So let us explore this and see. Give a different color. So you tell me in this set, okay, of 3, 4, 5, 6, you have done with 3. So, and you made a choice of 4 also. So you did 3, you did 4 also. So now what options you have here? I'll just draw it like this. Okay, you have 2 choices here. Can you tell me what 2 choices you have after this? With 3 and without 4. So what you should do?
5. 6.
Yeah, so with 5 and without 5. With 5, how will your answer look like? Just do the sum. Just do the sum with this one.
8.
8. Okay. So, and without 5, how will your answer look?
3.
Okay. So you can continue further, right? You finished 5, you have 6. So you have 2 choices. You will say with 6 or without 6. With 6, what will your answer be? 6 plus 8, right? 14, right? And without 6, your answer is 8.
8. Yes, ma'am.
Right. Any other thing you have? Any other child you can create out of this?
No, ma'am.
No, because we finished examining all the numbers, right? And anyways, none of these matched our sum. So we don't have to go back and trace it, right? So none of this resulted in the answer. So we go back, we here in the DFS, you come to this choice. So here again, you have 2 choices that you can do. What you can do? So you basically, the key is you need to understand what numbers you have to trace, right? 2, 4, 5, 6. You need to understand where we are correctly, right? For you to understand what numbers to take next. Just look at this. How did you reach here? You see, how did you reach? You picked, sorry, this is 3. Yeah, you picked 3. Then you chose this options and you chose this option. So you finished executing this also. You're left with only
6.
6. So you have 2 choices. With 6 or without 6. With 6, what will your answer be?
9.
Right. And without 6, it is
3.
3. Can you do any further?
No, ma'am.
No, because you finished the 6, right? You don't have. So again, you check none of these gave you 13. So you go back, and finally you come here, right? This again, you have to further expand. Maybe what I'll do is I will do it myself. You can follow and see if your answers match mine. Okay. I just need to draw a little wider. So this was without 3. So the sum is still 0 for me. Next, I have 2 choices with 4 and without 4. With 4, answer is 4. Without 4, answer is still 0. Now I have 2 choices here, right? With 5 or without 5. Here also I will have 2 choices. This you can expand it this way also. It is easy for you without 5. Okay. With 5 answer will be 9. Without 5 answer is still 4. Here with 5 answer is 5. Without 5 answer is 0. So I finished 5. I picked 6. Right. So I have 2 choices. With 6, without 6. Same thing. Everywhere I have 2 choices. With 6, without 6. With 6, without 6. Okay. So with 6 answer is 9 plus 5, 6, 15. Without 6 answer is 9. Here with 6 answer is 10. Without 6 answer is 4. With 6 answer is 11. Without 6 answer is 5. With 6 answer is 6. And without 6 answer is 0. Any of these resulted in what we wanted? Did any of this?
No, ma'am.
No, right? So we don't have to trace these paths at all. So finally, if you just look at the leaves, right, you can know, just look at all the last elements. Okay, that means this. You just have to see where you got 13, right? None of this gave you 13. Just look at the last element, then you will get your correct answer, right? So this did not give. So this is the only one which gave you 13, right? None of this gave you 13.